Welcome back, welcome back, welcome back. I'm Miss Lisa. This is my YouTube channel. This is chemistry class, and we are going to do the math that has to do with moles. This is our quantitative chapter 6, if you're doing this as a class. But you're welcome to be here, even if you're not doing it as a class. We're going to go through a lot of the math and chemistry, and hopefully you'll understand it. If you're doing this as a class with me, it's primarily designed for homeschoolers, but anybody can do it who wants to. But I want you to take 2 weeks on this chapter. We're not going to hurry this. I want you to take your time and make sure you understand this math, all right? So if you're doing this as a class, look in your book to page 143. We're going to do the 16, I think, example problems, okay? So these are all word problems. And what makes word problems hard? That's right, it's the words. So we have to get rid of the words and just know how to do the math. Okay, so our first one says, what is the mass of 90 average size apples? So over here, I write my knowns and unknowns, and mass is what I don't know. I know that we have 90 apples, and they tell me that a dozen apples, somewhere in here, equals, right there, 2 kilograms, is 1 dozen apples is 2 kilograms. Those are little apples. Because a kilogram is 2.2 pounds. I guess 5 pounds for a dozen apples. I guess so. I guess they're not that little. All right. So these are my knowns and unknowns. Okay. Now, when you do these problems, the first thing I want you to write down is what I call what you know, what you're given, not the conversion factor, not the question. Just what are you given? What do you know? And you know you've got 90 apples. So you write it down first, right here. Next, what we want to do is we want to convert these 90 apples to a mass unit. And we've got kilograms here, so that's what we're going to. How you do this is I want you to draw railroad tracks. Hold on a second. I'm going to get a pen that I can point with. Excuse me. Okay. All right, so you write what you would know, and then you draw railroad tracks. Now, some books like to show it with parentheses, but I've taught this for decades, and kids write so messy, their parentheses will turn into sixes, and then they get it wrong. So if you do these railroad track things I'm going to show you, and they really don't look like railroad tracks, they look more like braces or teeth or something. It just helps with the organization, okay? The other thing is like your book does it with using X for times. We don't do that anymore. Now that we've had algebra, we know that X is an unknown. X is not times. So I like the railroad tracks. All right, so you first write what you know, and then you write just the word of the unit that is what you know, you write down here. Then you write what you want to change it to, or what you can change it to, you write on top. And it's your conversion factor. What are two things that are equal that have this word? And we can know that if you have, that for apples, we can convert it to dozen, because we know there's 12 apples in a dozen. Now, so 1 dozen and 12 is the same thing. Mathematically, anything divided by itself is 1. So this is the math equivalent of multiplying our 90 apples by 1. And if you multiply anything by 1, you don't change its value. Now, do you have to understand that to do this problem? No. But for some kids, it helps to understand why you're allowed to do this. So step 1, write what you know. Step 2, write the unit of what you know down here. Step 3, write the unit that you're changing it to on top. And then write the relationship. 1 dozen is 12. So the mathematical relationship is 12 apples equal 1 dozen. Now, was I supposed to change it into dozens? No. I was supposed to change it into the mass, and we're going to do it into mass in kilograms. So I need to get rid of dozens, so I write them down here on the bottom again. So now I can write the relationship between dozen and kilograms. And I write kilograms on top. And the relationship is 1 dozen is equal to 2 kilograms. These are also the same thing. 1 dozen and 2 kilograms is the same. It's equal to 1. Now, any number on that is anything that's on the top and the bottom in math, you get to cancel out. So I can cancel out apples because they're on top and bottom, not the numbers, just the words. And I can cancel out dozens because they're on top and bottom. So any number on top here, I multiply. Any number on bottom, I divide. So now I do it on my calculator. I do 90 times 1 times 2, and then I hit enter, and then I do divide by 12, enter, divide by 1. But the ones you could skip because anything multiplied or divided by 1 is itself. So let's go over to our calculator. We're going to turn it on. I'm going to clear out what's in there so it looks nice and neat, and I'm going to put it in. 90 times 2, I can skip the 1, equals, now I hit enter. Now I'm going to do divided by 12, and it tells me the answer is 15. And so what's left is 15. That's 15 kilograms. Put a box around your final answer. Make it look pretty. Check it if you can. And I got it right. So yay! Always cheer for yourself when you get it right. All right, that was example 1. That was easy. And there's more of them here for you to practice. Okay? So moving right along, we go to example 2. Okay, this one says, how many moles? So I write down mole, question mark. We first list our knowns and unknowns. How many moles of magnesium? So I wrote down magnesium, and I wrote down the molar mass of magnesium from the periodic table, but it turns out I didn't need it. I sort of headed off on a tangent, not needed. A lot of times you do need it when they tell you what it is, but it didn't hurt me to write it down, but it was unnecessary. How many moles of magnesium are in 3.01 times 10 to the 22nd atoms? So I write down 3.01 times 10 to the 22nd atoms, and that's in scientific notation, and I'm going to show you how to do that on your calculator. It's a shorthand for us to communicate really big and really small numbers to our calculator. Okay, so we want to know how many moles, and we have atoms. What do we write down first? Say it out loud. What we know. And what we know is 3.01 times 10 to the 22nd atoms. Now we write the unit of what we know on the bottom because we want them to cross out. And then we say, is there a relationship we know between atoms and moles? Yes. 1 mole is 6.02 times 10 to the 23rd atoms. Atoms cancel out, and I'm left with moles, which is what I was supposed to do. Any number on top, you multiply. Any number on bottom, you divide. So it would be 3.01 times 10 to the 22nd times 1, but we don't have to do ones because they don't affect it, and then divided by this. So let's show how to do these on our calculator, okay? So I'm going to clear out what's in there so it looks nice, and I'm going to put this number into my calculator. This is how you do it, 3.01, and now you do not hit times 10 up arrow. The reason why is your calculator will think that's 2 numbers instead of 1. And sometimes it works out okay, but sometimes it doesn't. And if you will just get in the habit of always using the scientific notation button for scientific notation, it'll save you a world of hurt, as my daddy would say, which means later on, you're going to end up missing a college problem, and you're going to end up getting a bad grade just because you didn't use that button. Okay, so on your calculator right there, painted behind the comma is a button that says EE. That stands for times 10. How we get to it is we do second comma, and it puts a little E up there to stand for the times 10. And then we put 22, because that's the exponent, and you don't do up 22, you just put 22. Your calculator knows that this number is that number, and that's how we tell it to our calculator so it knows what we're talking about. Now we say numbers on bottom we divide, so I'm going to hit divided by, and Avogadro's number is also a scientific notation number, so I'm going to put it in 6.02, and then times 10 is second comma, that's our E, and then it is 23rd power. So I hit enter, and there it is, 0.05. So 0.05 moles, because atoms cancel out and I'm left with moles. Now your book weirdly put it in scientific notation, but not even correct scientific notation. Correct scientific notation would be 5 times 10 to the negative 2, but they did change it to 0.5 times 10 to the negative 1. I think the reason why your book's all crazy like that is because they think that you don't have a calculator and you're trying to do these without a calculator. But you have a calculator. You're going to buy yourself a TI-84 graphing calculator. It doesn't have to be as fancy as mine and be able to graph in color. Let's see my pretty color graph. But you need to have one of these calculators. The more time you spend with your calculator, bonding, or at least learning how to use it, the better you're going to do in college. Algebra, pre-calculus, calculus, physics, chemistry. The calculators are not intuitive, so you need to get them early in high school and start practicing with them. And I have a whole series of videos on how to use the calculator. They're called Calculator Labs, and they're in my Algebra 1 and Algebra 2 playlists. So make sure you go watch those too. I might make a separate playlist just for the calculator too. All right, let's move right along to example 3. Okay, example 3. How many molecules, all right, molecules question mark, we want to get rid of the words and make it more simple. Too many words make it confusing looking. How many molecules are 4 moles of glucose? 4 moles of glucose, okay? So what do I write first? That's right, what I know, 4 moles. What goes on the bottom down here? The unit of what I know, mole. What do I want to change it to? Molecules. Do I know the relationship between moles and molecules? Why, yes, I do. 1 mole is 6.02 times 10 to the 23rd molecules. Moles will cancel out, and I'm going to be left with what I wanted, molecules. Any number on top, I multiply. Any number on bottom, I divide. So let's do it on our calculator. Let's go. I have to get off of my graphing screen I got all happy with. I'm going to clear it out so it looks nicer for you. And I'm going to do 4 times 6.02 times 10, which is the E, 23. Ta-da! And we got 2.4 times 10 to the 24th molecules. And once again, your book's got a weird unit, but then they put it in the right one down there. Maybe they did in the other one too. Yeah, they did put it in a more reasonable scientific notation on the other one, but there's no reason to. That number right there is just fine. Don't do unnecessary scientific notation. Use it when it's needed, what it's good for. That's the thing I told you about. That's a mole of carbon, a mole of sulfur, a mole of mercury, and a mole of iron. See, all of that's a very convenient measurement for lab. There's the mole of sugar and the mole of water and the mole of mothballs. I told you the story about the poor girl who had to leave in an ambulance because I did a lab with mothballs. It was in the book. I had no idea someone would have life-threatening allergic reaction to that. I don't even use mothballs in my house because of that. I have never had anything to do with mothballs from that day forward. All right, so let's look at our new problem. Example 4. What is the gram molecular mass? Remember, I call that molar mass. Molar mass equals what? Of hydrogen peroxide. And hydrogen peroxide is H2O2. Okay, to figure this out, what we do is first we list the atoms that are in hydrogen peroxide vertically, HO. Then we look on the periodic table and we find the mass of these. So let me get my other periodic table book here. I'm going to lean down. Sorry about that. I should have had this out already. I always tell kids the most valuable piece of equipment in any lab is the periodic table. All right, here's the periodic table. So we're going to go look at hydrogen, and if we round it off, its mass is 1. And then we need oxygen, and if we round off its little decimal number, it's 16. Okay, you saw where I got this from? Okay, now I'm going to move that periodic table out of the way. Okay, so first you list what you've got, H's and O's. Then you look up the mass off the periodic table, 1 and 16. Then you multiply it, and I did use an X for time. I should have used a dot, by how many you have. And that's the subscript. So hydrogen has 2, oxygen has 2. Then you multiply. 2 times 1 is 2. 16 times 2 is 32. Then you draw a line just like you would in 3rd grade and a plus sign, and you add them up. 2 plus 32 is 34. And the molar mass is in, the units is grams per mole. Gram/mole. Whenever you have units, you can do a slash for a fraction bar. When you have numbers, though, I want you to always do flat fraction bars. The reason why is I've taught for decades, and kids will start like this with 2/3, and in a skinny minute, what does it become? 213, and they get the problem wrong because they didn't use a flat fraction bar. So make sure that you only use the slash for units. All right, moving right along to example number 5. What is the gram formula mass? That means it's ionic. So that's what we need. We need the formula mass. We'll put a question mark. Of ammonium carbonate. And this is the formula for ammonium carbonate. Now, a word about these subscripts. See those parentheses? It's just like in algebra. If you have 2 parentheses x plus 4 in algebra, that 2 goes for the x and the 4. And to simplify this, you have to distribute that 2, and you do 2 times x is 2x, 2 times 4 is 8. And remember, you can't put them together, because to put them together, they have to have the same letters with the same exponents. But that 2 goes for everything inside the parentheses. Well, it's the same thing here. That little 2 means I have 2 nitrogens, and I have 2 times 4, which is 8 hydrogens. All right, so that's how you read it if it has the parentheses. Okay, so now what I do to get the mass here is I list the elements vertically that is in the compound. I have an N, an H, a C, and an O. NHCO. Then I look up their molar mass on the periodic table, just like how we did with oxygen before. And it's the decimal number on the periodic table, but we can round it off. And nitrogen is 14, hydrogen is 1, carbon is 12, and oxygen is 16. All of those are from the periodic table. The decimal number at the bottom of the little square is where you get those. Now we're going to list, we'd say times for all of them, and we're going to list how many we have. Well, for nitrogen, we have 2. For hydrogen, we have 2 times 4, which is 8. For carbon, we have just 1. And for oxygen, we have 3. See that little 3 right there. Now we multiply them. 14 times 2 is 28. 1 times 8 is 8. 12 times 1 is 12. 16 times 3 is 48. We draw our line. We put our plus symbol. We add them up. And that's the answer. 96 grams per mole. Yay, we did it. We check it over here. There it is, 96 grams per mole. Now, mine might look a little different than theirs. I think mine's better because it's more simple. But, and, okay. Now, the molar mass. Here's where the book says they call it for the gram formula mass, but they say some people call it just molar mass, and that's what I do. And all the science professors, all the chemistry professors I've ever had called it molar mass. And my little symbol for it that I'll write on the board is M&Ms, because M&Ms are delicious. They melt in your mouth, not in your hand. No, they don't give me any money for a sponsor. All right, so let's do a problem with this. This is number 6. And we are going to convert moles to grams, okay? It says how many grams, so we do grams, question mark, are in 7.2 moles of dinitrogen trioxide. You don't really know how to do this yet, but I don't think. My other class doesn't know how to do this yet. Maybe y'all do. I can't remember. Different books teach chemistry in different orders. But anyway, dinitrogen means 2 nitrogens, trioxide, 3 oxygens. So it's that. Okay, so what we want is the grams, and we can use the relationship grams per mole off of the mass off the periodic table. So that's what we got to get first. So we take our element, we write it vertically of what we have. We have N's and O's. we look up the mass off the periodic table, and the mass of nitrogen is 14 and oxygen is 16. We multiply it by how many we have. We have 2 nitrogens and 3 oxygens. 14 times 2 is 28. 16 times 3 is 48. We draw the line and put our plus and add them up. And it's 76, and now our unit here is grams per mole. Now we're going to do our conversion problem and write what we know. 7.2 moles. So we write 7.2 moles. We write the units of what we know on the bottom, moles. We write the units of what we want on top, grams. And then we think about the relationship. And the relationship between moles and grams is this. It's our molar mass, our M&M. Right? So, and the relationship is 76 is the number that goes with gram, and 1 is 76 grams per 1 mole, but the one's understood, of this is this molar mass of the periodic table. So we put 1 with moles, 76 with grams. Anything on top gets multiplied, anything on bottom gets divided unless it's a 1 and we get to skip it. The moles cancel out because we have 1 on top and 1 on bottom, and we multiply 7.2 times 76. So let's get our calculator, turn it on. Okay, clear out what's in there so it's nice and clean looking. Okay, and it's 7.2, make sure you can see the whole thing, times 76. Enter, and there it is. 547.2 grams, because the moles canceled out, and they did it with significant figures to 547 grams. So we look over here. They did it in scientific notation. There's no reason. You can use scientific notation to show sig figs, but they just like to use it because they're nerds and it looks fancy. It's what I believe. The author of this book can contact me and disagree if they want to. Okay, find the number of moles. Here's our next problem, number 7. Find the number of moles. So our question mark is moles, question mark, in 92.2 grams. So we write down, where's our 92? We need to write that down too. 92.2 grams. We write down what we know of iron 3 oxide. And so the formula they tell us is Fe2O3. So to be able to convert to convert to moles from grams, we have to have this relationship of the periodic table that relates grams and moles. So we take our elements, list them vertically, look up the molar mass off the periodic table. Iron is 55.8, oxygen is 16. How many irons do we have? We have 2. How many oxygens do we have? We have 3. We multiply them across, and then we add them up. And that's our grams per mole of iron oxide. Okay, now we write what we know, our given, which was this, 92.2 grams. We draw our railroad tracks, and we write the unit that we're given on the bottom. We write the unit we want on top, and we think about, is there a relationship? And yes, there is. It's 159.6 grams per mole. 1 goes with mole, 159.6 goes with grams. The grams cancel out. We're left with moles. Any number on top gets multiplied. Any number on bottom gets divided. So let's do it on our calculator. And we can skip the 1. Okay? I'm going to clear out what's in there. And I'm going to put in 92.2 divided by, because it's on bottom, 159.6. Enter. And it's 0.577. 6 moles. And they rounded it off. The book rounded it off to approximately equal to 0.578 moles. Ta-da! We got it right. Yay, go us. All right. Now the gas at STP. And remember I told you it doesn't matter what kind of gas it is. They all have a volume of 22.4 liters per mole. So let's read our question. Determine the volume in liters, volume question mark, of 0.6 moles of sulfur dioxide gas at STP. It's not Stone Temple Pilots or standard oil STP oil treatment. It is standard temperature and pressure. Okay, so what we do is we know that of any gas, we have 0.6 moles gas. Of any gas, 1 mole is 22.4 liters at STP. So any gas. So we write down, first of all, what we know, 0.6 moles. We write the unit of what we know on bottom, moles. We write the unit we want to convert to, which is liters on top, and we write the relationship. And it's 1 mole is the same thing as 22.4 liters. Moles cancel out because we have it in the numerator and denominator. Any number on top gets multiplied. Any number on bottom gets divided. These are both on top. They're going to get multiplied. 0.6 times 22.4 equals 13.44. Rounded off, 13.4 liters. Liters is what's left. Yay, we did it. Yay, we got it right. We're awesome. All right, let's do another one. Told you there's, I think, 16 example problems. Whew, but just think of all the fun math you're learning. All right, this time we're going to convert volume of gas to moles. So determine the number of moles. So I'll write moles, question mark, in 33.6 liters. 33.6 liters of helium gas. But remember, we don't care what kind of gas it is if we're doing volume. Any gas is always the same. So what do we write down first? What we know, 33.6 liters. We write the unit of what we know in the denominator because we want them to cancel out. We write the unit of what we want to change it to on top, moles. Then we think, is there a relationship between moles and liters? Why, yes, there is. 22.4 liters in 1 mole. Any number on top gets multiplied. Any number on bottom gets divided. So we put it in our calculator now. Let's clear out what's in there and put it in. It is 33.6 divided by 22.4. And the answer is 1.5 moles. Ta-da! Ta-da! We got it. Let's do number 10. It says the density of a gaseous compound of carbon and oxygen is 1.964 grams per liter. So we're told density is 1.964 grams per liter at STP. Determine its gram formula mass. Determine its molar mass. And molar masses are in grams per mole. Is the compound carbon dioxide or carbon monoxide? Well, we're going to figure it out. So what do we write down first? What we know. We write it right here. Now, this one doesn't just have one unit like everything else does. It has a numerator and a denominator because it's grams per liter. So grams go on top, liters go on bottom, and 1, it's an understood 1. If there's just a letter in the denominator, you put a 1 with it. So it's 1 liter on bottom. Okay, now then we want to get, we've got grams per liter, we want grams per mole. So the grams are okay. What we need to change is we need to change to moles. So we need the liter to go away. So we write liters in the numerator so those can cancel out. We want the liters to be changed to moles, so we put moles in the bottom. And then we think, is there a relationship between moles and liters of a gas? Yes, there is. 1 mole is 22.4 liters. Liters cancel out, and we're left with grams per mole. So we do 1.964 times, because any number on top is times, any number on bottom is divided. We multiply it times 22.4. So let's do it. We'll clear out what's in there. Okay, so we've got 1.964 times 22.4. And it's 43.99. They're probably going to round that to 45. And yes, they did. 44. I said it wrong. 43.99 to 44. They rounded it to 44 grams per mole because that's what's left. And we go check over here, and there it is. Ta-da! So we got 44 grams in 1 mole. Okay, next idea. How many carbon atoms, so that's our question, how many carbon atoms are in a 50 carat diamond? 50 carat. That is pure carbon. And so it's 50 carat of carbon. Then they tell us 50 carats is the same as 10 grams. So I put equals 10 grams. All right. And I also looked on the periodic table. And because I know whenever I see grams, I'm going to need that molar mass off the periodic table. So I go looked it up, and the molar mass of carbon is 12 grams per mole. All right. So now I start with what I know. And what I know is I've got 10 grams of carbon. So I write it here. I put the unit of what I have on the bottom that I want to get rid of, grams. And I put the unit of what I want on top, moles. And you're like, but wait, we don't want moles, we want atoms. Whenever you change from grams to atoms or grams to liters or anything like that, you have to go through the Buddy the Elf revolving door of moles. That's what I was talking about, the revolving door. You have to change to moles first, and then you can change to atoms. So I put grams, from my molar mass off the periodic table, I put 12 grams on bottom, 1 mole on top. The grams cancel out, and I'm left with moles. But I didn't want moles, I wanted atoms. So now I got to get rid of moles. And I put moles on the bottom. I can put atoms on top because there's a relationship. 6.02 times 10 to the 23rd. Sometimes it's listed 6.022. The old book I used to teach, I've always did the second two, but your book only does one, is the relationship between atoms and moles. One is the number that goes with moles. Avogadro's number is what goes with atoms. Grams cancel out. Moles cancel out, and you're left with atoms. Any number on top gets multiplied. Any number on bottom gets divided. You could skip the ones. Let's do it on our calculator. Okay? Oops. It died out. Come back on. Come back on, calculator. There you go. I'm going to clear out what's in there so there's nothing to confuse you. I do 10 times 6.02 times 10 to the 23rd times 6.02. Second comma is the times 10 to the 23rd. Go ahead and hit enter. Get that answer before you say divided by 12. The reason why is your calculator has a hard time knowing what's getting divided by 12. Is it the 10? Is it the Avogadro's number? Or is it both? If you hit enter first, you'll get the right answer. And it's 5 times 10 to the 23rd power. 5.02 times 10 to the 23rd power. Ta-da! We got it. All right. Now, if you don't want to hit enter first, the other way you do this is you can put it in like this. You can say alpha y equals, select number 1 off the pop-up menu, which stands for make it a fraction, numerator, denominator. And it gives you this little blinky thing. And then you could do 10 times 6.02 to the 23rd power in the numerator. You can arrow down to the denominator and put 12 and hit enter, and that will give you the right answer too. For a lot of older calculators, their pop-up alpha y equals menu doesn't work. You can get an update if you go to the TI website, the Texas Instrument website, and get your parent to register as a teacher. And then they can download the update for your calculator, which will give you the pop-up menu. No matter how old it is, you can get that pop-up menu if it's an 84. The other way you could do it is like this. You could do, whoops, I messed up. Delete that. Delete. All right, you could do beginning parentheses, 10 times 6.02 to the 23rd, and then say divided by 12. And if you put this all in parentheses so that the calculator knows it all goes together, you'll also get the right answer that way. So, 3 ways to get the right answer. Okay, moving right along. We're doing good. We're on 11. We're getting there. Example 12. An 8.2 gram piece of magnesium, so I'll write down 8.2 gram magnesium, combines completely with 5.4 grams of oxygen. 5.4 grams of oxygen, wrote that down, to form a compound. What is the percent composition? Percent composition equals what? Okay, how do you do this? Well, the first thing you got to do is you've got to know total how much these are together. And it's because we have a law of conservation of mass. Matter can either be created or destroyed, only change from one form to another. So whatever we put in is the amount of matter we're going to get out, and we can find out what that is. So we put in 8.2 grams of magnesium and 5.4 grams of oxygen. We add them up, and the total mass that we put in and the amount we're going to get out is 13.6 grams of oxygen. 13.60 grams of our compound. Okay, so that's what you do first. Second, you list your elements in your compound vertically, just like how we've done in a bunch of problems. Then we write how much we have of each one. We have 8.2 of magnesium, and we have 5.4 of oxygen. And for each of them, we divide by the total because we want the percent, and that's how you get percents. You put the part on top and the whole on bottom, divide and multiply by 100. So magnesium divide by the total times 100, oxygen divide by the total times 100. So this equals, so let's do it on the calculator so you can make sure you know how to do it, clear it out. So here is my magnesium, 8.2, divided by the total, 13.6, and then I multiply it times 100. You don't use the percent button, you just do 100, and you get the answer. It's 6.29 percent. We rounded it to 60.3, and now we can do the oxygen. 5.4 divided by 13.6 times 100. And the oxygen is 39.7%. Now you can check that you did it right. That if you did it right, if you add these up, it should be 100 because together they should make 100%. Now 100 is not the answer. The answer is 60.3 and 39.7, but that's a check. Okay, let's do another one. Calculate the percent composition of propane. So that's propane. What I want is the percent composition. I list my elements that are in it vertically. So I've got C and H. I write down the mass off the periodic table for them next. Carbon is 12, hydrogen is 1. And then I do times how many I have. I have 3 carbons and 8 hydrogens. I multiply them, draw my bar, draw my plus sign, and add them up. So the molar mass of this, the total, is 44 grams, okay? Now, I take each of the parts and I list them down here. Carbon, 36, hydrogen, 8. And I divide the part by the whole, the part by the total. So each of these I divide by 44 times 100, and I get the percent of carbon is 81.8, and hydrogen is 18.2. And I can check, and those added up to 100, so I didn't have any big mistake there, right? So those are a lot the same. Okay, example 14. Calculate the mass of carbon in 82 grams of propane, and propane is C3H8, okay? So I want the mass of carbon in propane, C3H8, and I have 82 grams of propane. Now, before I can do this problem, I need the molar mass of propane, so I have the whole. So I list my elements vertically, carbon and hydrogen. I look up their molar mass on the periodic table. Carbon is 12, hydrogen is 1. I multiply it by how many I have. I have 3 carbons and 8 hydrogens. I multiply it and add them up. 12 times 3 is 36. 1 times 8 is 8. 36 plus 8 is 44. So that's my total mass. Now I list them again over here. This is my carbon, and I could do hydrogen, but notice they only ask about carbon. If you needed if you needed both of them, you would list them again, but this time they only care about the carbon. So we put the part of carbon divided by the whole, times 100, and we know that the carbon is 81.8%, and we could even figure that out by subtracting from 100 to get the hydrogen. Now they want to know how many grams that is. We have the percent, but we don't have the grams, and we can do this. It's just a regular is of percent 100 calculation, because we want to know what is the number of grams of 82 grams that is 81.8%. So this is our formula. Is of equals percent 100. Is what we don't know. We know the of, the 82. We know the percent, 81.8, and 100 is 100. We cross multiply and solve for the one we don't know. So we can do it on our calculator. Okay, I'm going to clear out what's in here so it looks better. So I'm going to do 82 times 81.8, 82 times 81.8. And then on the other side, I have x, our unknown, times 100. And so to get x by itself, I do the opposite of multiplying times 100, and I divide by 100. And it's 67 grams. So let me show you what I did there a little bit more clear. Okay, my is my unknown, so I'm going to make it x, because x's are unknown in algebra, right? 82 is my of, 81.8 is my percent, and 100 is 100. So now I'm going to cross multiply. I draw my little crosses there, and I have 100x on one side, and I have 82 times, it's hard to do through the calculator, 81.8 on the other side. I multiply these together, and I bring down what I didn't mess with, 100x equals 6707.6. Why is x not alone? It's being multiplied by 100, so I do the opposite. I divide by 100. What I do to one side, I do to the other, and then my x is 67.076. And that would be grams. Ta-da! All right, we're doing good. 14. We've done 14 math problems. Let's make it 15. Okay. Sorry, I needed some water. Okay. What is the empirical formula? Remember, that's the reduced formula of a compound that is 25.9% nitrogen and 74.1% oxygen. So last time we found the percents. This time we have the percent, and we're trying to get the formula. So what you do is, we could have any amount of this substance, any amount in the world, and it would still have the same formula. You can have a drop of water and it's H2O, or you could have an ocean of water and it's H2O. So the amount doesn't matter. We could have any amount, and what we're going to do for convenience is we're going to have 100 grams. Because if we add these two things up, they're 100. And if we change it to grams, then... Excuse me, I fought that sneeze, but that sneeze won. Anyway, we can pick any amount, and we pick that we have 100, and that way we can change these percents to grams. So we are given these percents, and we're going to put them in grams, and what we're trying to find is empirical formula. So this is what you do. For each one, you first list your elements vertically, and then you write what you know, what you were given for each one, and we have 25.9 grams of nitrogen and 74.1 grams of oxygen. We draw our railroad tracks because we want to change these to moles. And we look on the periodic table and find the molar mass on the periodic table. Nitrogen is 14 grams per mole, so grams goes with 14 goes with grams, 1 goes with the moles, and oxygen is 16 off the periodic table, grams per mole. Grams are going to cancel out, and for both of them, we're going to be left with moles. I get 1.85 moles here and 4.63 moles here. Next, you look at your two answers and you say, which is less, 1.8 or 4.6? Well, 1.8 is less, so this is the winner of being less. Now we write these down again over here, nitrogen and oxygen, and we write how much we had of each. Nitrogen is 1.85, oxygen is 4.6. The one of these two that is less, we divide into both of them. So we divide 1.85 into both of these. 1.85 divided by 1.85 is 1. 4.63 divided by 1.85 is 2.5. Now, if these are whole numbers, they become the subscripts for the empirical formula. So if this had been 1 and 2, the empirical formula would be NO2, but it wasn't. It's 2.5. And 2.5 is too far to round for this. So instead, we have to double these to get whole numbers. 1 times 2 is 2. 2.5 times 2 is 5. So 1 times 2 is 2. 2.5 times 2 is 5. And these whole numbers become our subscripts, N2O5, and that's the answer, the empirical formula answer. Okay, let's do another problem. Calculate the molecular formula of the following compounds. And I'm just going to do A. You can look at their B and C, but I think A will be enough. Okay, so this is how you do it. This is what we're going to calculate the molecular formula for. So we are given the CH4N, and we write it vertically. They tell us what is the mass of this, and it's 60. So we'll write up here 60 grams. All right, now we have to, for each of the ones we have, we look up their mass on the periodic table. 12 is carbon, 1 is hydrogen, and 14 is nitrogen. I should have written it the other way. I don't know why I did it that way. I'm a little dyslexic and dysgraphic, and I'll write things backwards and flip them. So there you go. I flipped it. The 14 should have been there and the 1 there, but you can just pretend it is. All right. Then we write how many we have. Carbon we have 1, hydrogen we have 4, nitrogen we have 1. We multiply them out, and what are we going to do? What we've done every time, we're going to add them up. 12 times 1 is 12, 1 times 4 is 4, and 14 times 1 is 14. Added up is 30 grams. We have 60 grams. So now we want to see how many times 30 goes into 60. So 60 divided by 30 is 2. So we double all of the numbers on the bottom. So C has an understood 1 there. 1 times 2 is 2. 2 times 4 is 8. And 2 times 1 is 2. And that's the real formula, for the molecular formula for this compound. Woo, we did it. Boy, that was 46 minutes, but we made it through all 16 example problems. I want you to take 2 weeks learning this. We're not going to hurry it. I want you to practice these problems. I want you to do problems and then check your answers till you get good at it. And I want you to become an expert at this math. It's pretty simple if you just get down some of the basic ideas. It's not like there's really 16 completely different problems. They all have similar elements to each other, but that makes it tricky too. All right, so I want you to like, share, subscribe. I'm Miss Lisa. Math is great. Chemistry is great. Science is great. Come back for the next video.